Sure. I guess first, everyone, happy holidays. Thanks for joining us this late in December, and hope you guys have a great rest of your holiday season. Second, this is our man Clyde. One of our customers, Humanetics, fabricates crash test dummies. They're one of the industry leaders in the area. They use our printers for a bunch of things. They have an X7. They use them for molds and fixtures and all that kind of stuff. One thing they're doing that's a little more exploratory is trying to print out parts of their dummies. So they were kind enough to, after this was tested in Europe, I believe, at a crash test dummy qualification site, have Clyde retire at the young age of 4, I think that's the age here, to our webinar chair. So you can come accompany me as I talk about H13 Tool Steel, which is pretty exciting. So yeah, with that, Marco, I'm just going to get started. If you guys have seen our webinars before, you might notice this is a little bit different of a format, or a little less. We're going to be a little less structured here. We're going to talk a little bit more just about the materials, and we're going to rely a lot on Q&As. So please have those questions flow in. We're happy to answer them. We have a bunch of information that we want to present as you guys ask for it. We've done this a couple times before, and we've found that it's a little bit more engaging than a typical kind of just we talk at you webinar. But before we get to more question and answers, I just want to give a brief overview of what we're talking about today. So super simple agenda. We're just going to talk about the Metal X just for a refresher of the entire system, give you a whole overview. We're going to then talk a little bit about H13 and some things it's good for, some of the characteristics we have, and I have a little bit of data to show on this presentation. And then largely I'm just going to open up the Q&A. So if you have questions about H13, the Metal X in general, even our composite systems, I'm happy to answer. Marco can also help with the more procedural questions about where you can get recordings and all that kind of stuff as well. And so for what it's worth, we are recording this. We'll post it on our website just like any others, and we'll send it out to you, as Marco said, in the near future. So with that, let's get started. So the Metal X. So we shipped the Metal X almost 2 years. We announced the Metal X almost 2 years ago. We started shipping it about 6 months ago. Just a quick refresher on the system. The Metal X is a bound powder extrusion metal system. So if you compare that to kind of the main systems that you see out there today, which are selective laser melting. Selective laser melting relies on a powder bed where they spread powder and then they use a laser to selectively melt parts that they would call units called voxels into a discrete part. There's a bunch of things that happen with SLM. One, it's really difficult to manage the powder. Two, the machines themselves are very expensive. They're in like 500K to $1 million plus to millions range. And three, you have some issues with part characteristics and warping, and requires a lot of post-processing and heat treatment and all that kind of stuff. So metal printing in the past, and I say this in the past because really we've taken a huge step forward in the last 2 years as an entire industry, was really kind of pigeonholed as this thing that Fortune 500 companies would use to put in an R&D lab and test some new stuff, and maybe occasionally have a couple of big parts. So the Metal X system is part of a new wave of metal systems. So when I say bound powder extrusion, what I'm saying is we still, at its core, there's still the same powder inside of our system. The metal powder is still the base of the system. But instead of having it loose, spreading it in a bed, and then using a laser, what we do is before we print, we bind the powder in a waxy polymer that basically makes it not look like powder anymore. It's kind of a clay-like filament that you would expect that is the exact same material or very similar material that you would see in a metal injection molding process. And so metal injection molding, for those who may not know, is the process that Apple kind of used to revolutionize small metal parts in their iPhone systems and all of these systems. And now it's rather ubiquitous. It was a rather unknown technology as recently as about 20 years ago. And what it is you have metal powder encased, you heat out, you basically melt the metal polymer, you put it in a mold, you take that mold out, and then you post-treat it to make it metal. We do the same thing. So where they would just shoot it into a mold, we extrude out a filament like we know best with our composite printing background, and that yields you with the green part. You then take the green part, you put it in a washing system, which is this nice looking box to the right. And so what that does is it's pretty similar. It's a debinding. We have a debinding agent that circulates in there, dissolves most of the binder from this part, leaving mostly just metal powder and a little binder left, and creates a bunch of tiny little pathways inside this part. So then after you take the part out of a washing station, which usually takes about 24 hours to 48 hours, depending on part size, sometimes a little more, we put it in the sintering oven. The sintering oven then basically burns away the rest of the polymer, which then escapes through those tiny channels that were opened up during the wash process. As it burns it away and heats it up further, those channels shrink and disappear as the part becomes near fully dense, about 94% dense. And as we reach the peak sintering temperature, which is about 85% of the melting temperature, that part becomes, the metal powder in there that was kind of next to each other, kind of hanging out, becomes a full metal part. And so when you get out of that is a part that looks like this. The camera is probably looking very small in this, but we can show a little more detail later. We have full metal parts. The thing about our part, the one unique thing about this process that I call bound powder extrusion, we've called ATOM in the past, you've seen as bound powder deposition is another word, is that it produces parts that are kind of similar to plastic in structure. And what I mean by that is you have walls, roofs, and floors, but the core of the part is still a hollow infill. We can do solid infills to a certain size. The reason we do hollow infills is twofold. From a practical perspective, you need most of the strength of a metal part on the outside. So actually what we're doing is we're taking a heavier metal like steel and we're making a more weight efficient part. And from a more practical side, with washing and debinding, you can only debind to a certain depth basically. And so when you look at metal injection molding parts, the technology that kind of fathered this technology, the parts that are primarily metal injection molded are very small. So to allow us to print these larger parts, like something of this size here, you need to have slightly hollow infill that then allows the debinding system to dissolve most of the wax in the sintering system to burn it away. In that sintering process, there's about a 17% shrink, but it's easily calculable, and we account for it in our own process. So yeah, so that's a little bit about the Metal X. Again, we started shipping it in about May of March or somewhere early this year. We've shipped, I think, about 100. We're on pace to ship more than 100 units by the end of the year. We have customers out there using it, and it's really exciting. The material they're currently using is 17.4 pH stainless steel. That's kind of that was a launch material. Great general use stainless steel, precipitation hardened. Generally, like in terms of stainless steels go, is pretty hard, pretty stiff, pretty robust, a little brittle, but overall a great first material. In this webinar, the purpose of it is to talk about the second material, which is H13. So these are just a couple small things in H13. I can dig up some more stats later. But the thing you're seeing on your left is the microstructure of the sintered H13, which is about 95% dense. And the right is kind of a material chart of what we're looking at here. So H13 is a tool steel. It's quite different than 17.4 as a stainless steel. So all tool steels are generally hotter and stiffer, are hotter and stronger than stainless steels, and generally used for tooling of some sort. H13 itself is a hot work tool steel, which means that it's a little less hard than a cold work tool steel like A2, which we'll have coming out in the coming months. But it's better for use in applications where you're heating stuff up, and in particular when you're heat cycling stuff. So when you're rapidly heating stuff up and cooling it down. So think molds. It's overall it's a material that reaches a Rockwell hardness of about off our printer 40. It's hardenable through our established standards to 45 and theoretically up to 50 or 52. So it's a pretty hard material. It's not like A2 or D2, which you'll see up in the high 50s, maybe even the 60s range for Rockwell C hardness. But overall, it's a great material for injection molds, for wear tooling, for anything that needs a little bit more robust surface strength than 17.4. And so that's kind of where we're at on this. In terms of where we compare to the main wrought heat treated, which is kind of your established standard for H13, what you see is that we are a little bit weaker, but it's a matter of, I think it's about 1510 with our heat treated versus about 1590 MPa ultimate tensile strength for H13 wrought heat treated. Our as sintered you see is a little stiffer and a little weaker. As you heat treat it, it gets stronger as you post heat treat it, as you would with any H13 tool you use normally. It gets stronger. As a byproduct of a MIM system is that the parts are generally don't elongate as well. So if you're familiar with our 17.4 data sheet or 17.4 data, you'll see something similar where a normal wrought 17.4 extends about 1 to 1.5% by unitless numbers before breaking, and ours goes about 0.5%. You'll see a pretty similar thing with H13 where it is a little more malleable. It's a little more, it can extend a little further in a wrought scenario than in a heat treated than a printed scenario. Overall, that's not a massive issue when it comes to usage. I guess the one thing I want to talk about before kind of opening up the floor to questions and kind of opening a dialogue with you and Marco and just letting you ask stuff is the heat treatment procedure. So first, so 17.4 is a kind of usually anneal. So there's a number of heat treatments you'll see for 17.4, which are H900 and H1150 are the two most common. We prefer H900, but as a whole, 17.4 is something where we recommend you heat treat it, but it's not necessarily required for the applications you're looking for. H13 is a bit of a different story. You really, really want to heat treat H13 to both relieve stresses inside a part and to make it harder. Interesting thing about H13 is it's a two-process heat treatment. You're heating it up to about 1010 degrees Celsius, somewhere between that and 1030, and then you're air quenching it, so you just leave it out in air and let it cool down. That's the raw quench state. If you use it in that state, what you'll get is a really hard steel, probably in the neighborhood of HRC 50 for our printed steel, but something that's a little bit, but something that's much more brittle. So generally what you do is you temper, or you even double temper the steel afterwards. The temperature you temper it at, a nice little alliteration rhyming sequence there, has a pretty heavy control on both the toughness of the steel, so how much bend, how much malleability you're going to get, and the hardness. So what we recommend is about a 600 degrees C temper, and what that yields is that 45 HRC that you'll see on our data sheets if you've seen them before, and you'll see again if we are able to find it after the webinar, if Marco sends it out. Alternatively, if you temper it a little bit cooler, so say 530, for somewhere between 500 and 530 C, your Rockwell hardness will rise to in the neighborhood of 50. This is just general. This is general metal. This is not specific to ours. And so you can get a little bit harder of a steel. What you get there is then the toughness of the material by like an IZOD notched standard would drop significantly. So tempering it to a higher temperature gets you a lower hardness but higher toughness. So that's kind of just an overview of the space there. And there's plenty of literature out there about tempering temperature versus toughness and hardness. I'd recommend if you want to use H13, and I'm sure you already do, you can kind of look into it. Our stuff generally holds true to what those standards are. I would say that by nature it's a little bit less hard than wrought, but not by a significant portion. We're talking like maybe in a heat treated state, we're talking like 1 to 3 like HRC difference. So with that, that's all I really explicitly have. I guess I can show off these applications that we're talking about in the table in front of me, but I think it'd be easier if we just end the presentation and go full screen for video and just do a Q&A. So Marco, do I have to stop share?
Give me 1 second. We're going to cancel this.
All right. So 1 second, please hold. All right. And yeah, so I guess just in terms of applications, as we said, it's just another strong, it's another metal. It's a bit harder. It's a bit stronger. It's used for more tooling. So something like this, or this is these are seated tools, which we'll see a little bit better when Marco full screens, can basically last longer than a 17.4 tool that would wear away faster. Let me put this back.
So we are full screen. I'm going to zoom in on these.
We are full screened?
Yep.
All right, cool. Let me just stop the share on mine so I can see myself. All right, cool. Sorry, a little bit of technical details. Yeah, so you can see here, so these inserts are printed out of H13. This part here is actually printed out of our thermoplastic onyx. You will basically have an onyx base, which is strong, which is fiber reinforced. Then you have H13 pads on top that are actually what's interfacing with the harder metal material. So if you're using something like a casting machine thing, you're trying to inspect it, that's what you can do. You can print end-use parts like nozzles here. We have a pretty precise machine because of the FDM nature of it. You can print threads pretty well. You can also print stuff like impellers, although that's maybe less of an ideal use case and more of a show off of the actual material, the printing capabilities.
So it looks like someone's asking about surface finish. So I'm going to zoom in here as much as I can.
Yeah.
Try to see how well the camera can capture that.
All right, so we do have some questions now. So I just want to make sure it's formally open it to questions. Let's, if you have questions about H13 or Markforged in general or the Metal X, just feel free to ask away, and I'll answer them as best as I can. So we had a question about, let's see, are there different sintering gases required? No, there's slightly different. The sintering oven can account for both 17.4 and H13. Someone asked if we plan to release an aluminum material soon. It's something we probably have in R&D, but probably not immediately soon. Can you use traditional heat treatment to sinter the green parts? No. So the Sinter one, which is our sintering furnace, comes with the Metal X system as a whole. We use that to sinter it. In terms of heat treatment, the sinter doesn't currently heat treat, and I would actually not recommend to use it for heat treatment because it's probably more expensive to run than your typical furnace, and most people have furnaces. I would sinter it in the Sinter one and just use a standard furnace to heat treat. Let's see. Someone asked about the hardness of H13 on the Rockwell C scale. So as printed, it's 40. If you heat treat to 600, or at fresh quenched, it's 50. Tempered to 600 degrees Celsius, it's 45. And if you temper it to 530, although we have not formally released this as data, I believe you can probably push up into the 50 range.
So someone's asking if we can place a 17.4 part next to the H13 part. I think they're going to look pretty similar, but I can bring one over.
Marco can go grab one. The fact of the matter is that 17.4 and H13 look very similar. They're both steels. If you the one significant difference you would see is that 17.4 oxidizes in a way, H13 oxidizes in a way that 17.4 does not. This is your 17.4 part, and this is an H13 part here. They look just about the exact same. They're they're a little difficult to sell apart. The one nice thing that we do, which you're probably not going to be able to see in the detail here, but I can try, is we print rafts around all our parts, and because they do look pretty similar, let me see if I can pivot it, catch the light. Looks like I can't. Around each raft, we print just like a simple letter that refers to the material, so you don't accidentally sinter 17.4 parts with H13 parts, because they are different sintering settings, they are different sintering runs. So little things like that make it a little easier to use. What's the density of the finished part for H13? So the density, our density is about 95%, 94.5%. But as I mentioned before, what we're doing with most parts generally, there's my arms, is we're printing with open cell infill. So the actual density of your part is probably significantly less than that. For a very small part like an insert, it's higher. And you could print with certain walls and stuff like that to make sure it stays strong. But like the overall density is kind of variable based on your part size. 95% if you're able to print fully dense. Someone asked print resolution, minimum layer thickness. Right now we're printing. So right now, as Metal X is shipping, they're printing at 150 micron green, which means that after you sinter it, the effective layer height is 125 micron. We're expecting to push a 50 micron capability soon on the same hardware platform. It's just a matter of proving out quality. So that's coming in the near future. It will go down to 50 micron. I believe it's 50 green, probably 33, or no, sorry, like 42 sintered, but I'm not sure the exact numbers. Have these parts been finished post-sintering? These ones have not at all. These are right off the sintering oven. You absolutely can finish parts post-sintering. So we had a question on a similar webinar, a similar presentation to this recently that was, are they good enough to use injection molds right off the printer? The answer is no. You need generally to machine something for injection molds right away or to get it to work. You can actually post-machine these. We have some customers who have tested the post-machining and it has worked. We're working on enabling some features that will enable machining to be a little bit easier, so you can be selectively add more floors or roofs or walls, so that there's more to machine. But it is possible, it is doable. Someone asked when the next metal will be available. I don't know exactly, but it's in the near future. We're ramping up the launching of new metals as we do this. So we mentioned the piece would be hollow. Do you have an idea of weight difference? So with weight differences, it totally depends on the volume versus the surface area. So with printing, you have a surface area that's some arbitrary thickness, so that volume generated, and then you have an infill that's also basically some set density. So the ratio of those is kind of what determines the difference in weight. So if you have a part that's basically a big rectangle, that's going to be very different in weight. If you have a part that's a bunch of really small features that have like a lot of walls, my nice hand movements here, the weight will be different. If you have something that has thinner walls like this, the weight will be less different again. What's the price for H13? So I believe Marco can answer this maybe as well as I can. It's $229 a kilogram for printing. That's pretty consistent with market prices in line with our 17.4, which is $99 a kilogram for printing, if I remember correctly. Or maybe 130. I can't remember the exact prices, but it's that area. How close are we to printing with aluminum? Got a second question. We're probably a bit of ways from aluminum printing. That would be my guess. It's not explicitly in our kind of coming soon list. It's more in the R&D list. So let's see. Someone asked what kind of tolerances we can hold. So I would say I don't have I don't want to say something that I don't believe fully. On composites, where we know a lot more, we have a lot more printers in the field. I feel pretty confident saying we can hold like a 5,000, 125 plus or minus tolerance. On metal, theoretically, that number should converge pretty close to that. I don't know where it is currently. I would guess I've seen most parts that I've seen printed have been very accurate. So I think the end goal is to get it right near there, and I think we're getting pretty close to that. It's also, as any 3D printing is, the tolerancing is geometry dependent. If you print a nice rectangle where all the features are on the flat surface, they're going to be more accurate than if you print it on its side. Someone asked why we always print a raft. Is this a requirement for part building process or for post processing? I believe in production, either it is a requirement. It allows there's for a few reasons. It allows us to basically control the sintering surface better, so the part sits up better in the sintering surface. It allows us to control the support, so it's basically a held together ecosystem when the part's weaker. It also helps with part contraction. Any trials using this in die casting? So no formal trials, but because H13 is generally a tool steel that lends itself very well to both molding and die casting, I suspect, and this holds basically the same heat characteristics, it should absolutely work in die casting. There's no reason it shouldn't. You probably need to do the same post machining. What's the maximum part rate printed? Our Metal X spec, really the actual stage is spec for a 10 kilogram part. But again, I think metal printing in this sphere is most better for parts not in that 10 kilogram range. You can print big parts. It's probably better to print smaller parts. That's just the way the fabrication method lends itself to. Someone asked, can you wash 17.4 and H13 at the same time? Yes, it's the same solvent. So the washing is the same. The sintering is different. So you want to do sintering runs with like materials. You can put as much as you want in the wash. Someone asked, you mentioned shrinkage in the sintered part versus green part. Do we have to model it? No, our software accounts for that automatically. So it'll scale the part up as you print it. So I don't have any green parts next to me, but we have some good examples with the green parts that looks a little bit bigger, looks like 20% bigger than the sintered part, and then it shrinks down. Let's see. Sorry, questions are coming quickly. Post-processing required. So as I mentioned, most H13s are heat treated. So that's the main post-processing you'd see. If you want better tolerances, or if you want to machine something, you can. If you want to grind something, you can do everything you would want to do with the normal H13 part. It really depends on the application. So for a part like these cradles here, they need to be a little less accurate. So they're probably good right off the printer. No big deal. For a part like a nozzle or for a part like a mold, you want it to be very accurate. Therefore, you would almost certainly post-machine it. Let's see. Someone asked, what's the contraction rate? Sorry. How fragile are parts in the green state? So the parts are moderately fragile in the green state. It's not a huge deal. Where they're more fragile is what we call the brown state in between washing and sintering, but it's not something where they're going to disintegrate the moment you pick them up. It's more something where you just want to be careful with them and you don't want to load them in any way. Let's see. Oh, someone asked earlier, does a sintering oven use canisters or intended to be hard piped? We decided to kind of make our system the easiest to use as possible. Part of that is to do a more standard gas usage scenario. Marco is in here showing off the nozzle. So it is hard piped in, but when you purchase a system, we have resellers and we have technicians that help you install it in your own process. Yeah, let's see. Oh, someone asked, what's the how much material can you remove in post-processing? So this is something we're actively working on. Right now, so it's dictated by the number of roofs and floors you can print. So I think it's like we have a design guide that is actively updated for this. If you have questions that we can send out to you if you're interested. My base knowledge of it is that it's around 1 millimeter, so it's not a whole ton. It's enough that the tolerances we hold are good enough, but it's not for massive machining operations. I think we will do in the future is allow you to just like in composites, alter the number of walls and floors and ceilings so that you can make a thicker walled part if you want to machine more. Someone asked best surface finish in RA. I don't have the RA number, although I'm sure we could get it. The answer to the question again is that you probably want to post machine it, even if it's just moving not very much. Someone asked warping and cracking issues. For our parts, there are none. H13 is a little bit more susceptible to warping than 17.4 is, but as a whole, it's still because of the raft and because of the way you do it, it generally does not warp. If you have horizontal holes or pockets, how do you handle the removal of support material before or after sinter? I didn't talk about support material. Could work for myself. So if you looked at that part that we had just seen that was just on the table before, that motor mount, that kind of oddly shaped part, it had the raft below it that had included support material. So you actually sinter, you print, you wash, and you sinter with the supports on. The supports are like materials. This is also steel here. What is not here anymore is an interface layer. So normally on top of this raft here and below this printed part here, just get in frame, you would see basically a small ceramic release layer printed. And as you sinter, that release layer turns from a filament to a dust, and you just break it apart after sintering. It's worth noting that stuff like chunkable supports and little things like that are stuff we're still working on getting the stuff ironed out. So the support would have to be removable removable directly, geometrically removable. But if it's something like a hole, you can just pull it out with pliers. How long does it take to make the H13 parts in the green state? It's the same, virtually the same printing speed as H13. So ballparks, this part here probably took about 3-4 hours to print. A part like this, which is stainless steel, takes a little bit longer, probably close to 16, 17, 18 hours, a bit longer. Part like this, depending on the support material required, might take 6 to 8 hours as well. These inserts themselves are pretty small, so I would, if I'm ballparking here, I don't have the specific numbers. My guess would be this is something like an hour, if that. This is probably closer to 2 hours, 2 or 3 hours, and this is closer to 3 to 4 hours. So not massive times. It turns out that really what you're seeing when you're turning fabrication times is the print time plus about 1 day for sintering, regardless, plus about somewhere between a day and 3 days for washing, depending on how big the part is. Someone asked how long sintering cycle, just answered it. It's about 25 hours. And we're probably working time on getting that a bit shorter, but right now that's the cycle that allows us to yield the most successful parts. Yeah. So someone asked, what's the maximum size of component you can produce? Weight-wise is 10 kilograms. The Metal X, size-wise, it depends. So the Sinter 1 is a bit smaller than the Metal X. Its diameter is about 5.5 inches. So whatever you can fit as a green part in the Sinter 1. Again, we have a design guide. I can give you more detailed answers in the future. And so those are kind of the scale things. You can print long parts. You can print parts that are a little, like maybe 3.5-4 inches wide in the Sinter 1 and a little bit, and maybe 3-4 inches tall. We're also developing a Sinter 2, which has been in development for a while, shipping probably sometime in the next year, or in 2019, next calendar year. And that will be able to sinter parts that are as big as the Metal X can print. And the Metal X's print area is about 10 inches by 9 by 7. But if you printed a brick that big, you would almost certainly run into the weight issues. Someone asked if it's possible to get prototype parts printed from us. What's the lead time? So we don't. So two answers to this. One, we do not run a printing service per se, but we do a benchmarking program for people who are interested in purchasing a machine. So if you got in contact with your sales rep, if you ask in contact with a sales rep, we can put you in contact. They can help you work with one of our application engineers to get a benchmark part printed and sintered and sent to you, so you can actually see and qualify it. How hard is it to switch between metals from print to print? This is actually one of the biggest advantages between us and SLM type printers. With SLM, you have to kind of clean all the powder out. You have to vacuum everything. It usually takes somewhere between like a day and 2 days. Some machines take a little bit less if they optimize for it. With us, the time to switch between materials is just about the same as plastics. So you just take the material out, you put a new material in, and you make sure that everything and the nozzle wipes itself, so it stays very clean. It's worth noting you do not want to contaminate materials, so I would not recommend putting half a part in 17.4 and another half in H13. But it's not a hard material switch at all. We regularly switch our printers in the office to print benchmarks because we're printing benchmarks in different materials all the time. Let's see. So someone asked about toughness and impact resistance properties compared to pieces of forged or rolled. Due to the nature of the fact that it elongates less before breaking, I think it's probably a little less tough. I don't have the formal data for it right now. And yes, but I would say that it's tougher than 17.4. You can also anneal 17.4 to make it increase the toughness as well. It's probably it'd be a good question for an application specific thing. Someone asked about hardness again, so just to run through it one more time. As printed, it's 40 HRC. After you heat treat and temper to 600 C, it's 45. And then there's a couple ways you could get to 50. One is if you didn't temper it, which I would not recommend. That would get you about 50. The other one is if you tempered it at a slightly lower temperature. But it might be something where if you get a printer in-house, you can test heat treatments and see what works best for you. Because as you know, with H13 really runs the gamut from 38 HRC to 50 HRC in application, where softer ones are used for awareness, for applications that require more toughness, and harder ones are used for applications that require more hardness. So again, it's just a general heat treating question. Someone asked if you can print if we need a raft on a block that's 4 inches by 3 inches. I'm not actually sure we could print 4x4 by 3 right now, or we could sinter 4x4 by 3 right now in the Sinter 1. In fact, I think it's a little bit big. Might be able to do 4x3 by 3. What's the highest infill you can use? So again, I think the infill is currently set. I'm pretty sure the infill is currently set. The reason being that the wash time goes up exponentially by how much the solvent has to penetrate into a part. So you could quickly get to a part. If you print a cube that was 4x4 by 3 and you had to wash it, it might take an infinite amount of time to wash, or years. Can you weld on these? So in 17.4 we can weld, we can weld 17.4, which is notable because 17.4 is particularly not that weldable. I believe you can weld H13 as well, although we have not formally tested it. I do have a plastic mold example. I don't have one with me right now. We have a customer by the name of Grant Engineering who does injection molds. They tested the overall process with 17.4 just to see if they could like print molds and machine them, and that worked. And we're in the process of verifying H13 with them as a secondary material that they would actually use. One big advantage of injection molds is that you can print conformal cooling channels in our stuff. So our stuff can print to about 40 or 45 degrees with no supports, which means you don't have to remove them at all. So what you do is you design diamond shape diamond shaped channels that go through the part, that go close to the surface, that allow the mold to cool faster. So our value prop with molds is maybe less about a mold cost thing, because you still do have to machine it, and more about can you shoot molds faster and how much a process advantage can you get there. Let's see. Sintering time is the same. I believe it's roughly the same. I don't have a formal data on that. Do you need gas to reheat the part? No. Once it's an H13 part, you can just use a standard H13 sintering process and a standard furnace, which is why I would probably not recommend trying. I mean, you can't use the sinter one right now, but if you have a furnace, just use that. Let's see. Someone asked sintering cycle again. So about 25 hours for 17.4. I believe H13 is pretty similar. Someone asked support filament used and filament diameter. So as we said here, the support material is like material, and the key is that the separation layer is a ceramic-based thing that turns to dust when you sinter. The filament diameter, I don't think we disclosed that, but it's a pretty standard printing filament, although it's metal, not plastic. Is the green state scaling feature in Eiger dependent or global? If you were sliced apart composite, it would not scale. If you slice it in metal, it would. Any metal part would automatically scale as you need it. You do not need to scale the part. You can scale parts if you want to make them larger or smaller, which we do if you're not printing something that's has dimensional requirements, but not explicitly. You don't have to do any extra work there. Let's see. I don't see any more questions. Marco, do you see any more questions? Oh, sorry. I see one more that's does software automatically control the generation of supports and raft depending on the geometry? Yes. So it will automatically do the raft and the supports for you. It will show those parts. It'll show kind of what it generates before you print it, and it'll print it as such. Yeah, I don't think I see any more questions. Does anyone have any more questions? All right. I think we're good on question. Someone asked again about surface roughness. We kind of covered this. I don't have formal data on surface roughness, but you can machine these parts if you want something that's more precise finish. And again, hardness. I believe we already we talked about this question a bit. Yes, you can. So you can get up to 50 HRC if you post treat in a certain way, or if you quench without tempering. Can we print multiple parts at the same time? On composites, we can. Honestly, I don't know where the software is precisely right now. All logic tells me that we should be able to, and I'm 99% sure we can. There's no reason we couldn't print two parts at the same time, sinter them, and wash them. So
we can, yes.
Yes, we can. Just double checking. And then the other thing I wanted to note is that when you're sintering parts, you don't have to sinter just one at a time. You can sinter as many as you can fit into that build area reasonably. And yeah. So that's so pretty easy process. The sintering and the washing are both batch processes, and the printing is a process that you can parallelize if you want. Yeah, what's the set infill? I wouldn't say it's easy to quantify. I mean, it's basically just a set triangular infill with a certain size. We could get you the specific size if you have that question, and we can follow up with you afterwards. It is triangular. It's I'm trying to scale it in my head. It's probably about 3 or 4 millimeter triangles with my guess, and just a standard crosshatch pattern inside. Someone asked if you're possible in nitride 3D H13 printed parts. I don't necessarily know, but if you can do it with a standard H13 part, you can probably do it with a 3D printed one. What's the minimum thickness we can manage? We don't recommend printing super small parts on the current platform. At some point, we'll probably upgrade our platforms to print thinner features. I believe the thinnest feature we'd probably recommend printing is somewhere in the 2 millimeter range, probably 1.6 is probably a more formal number, but it really depends on hardware upgrades that we're working on and software upgrades. But again, like not probably the best fit if you're doing for super precise stuff, but you can do something like this impeller, which is a bunch of very thin features itself. So when is an upgrade from for H13? If you're a customer, the H13 upgrade should be coming out very soon. The material should be available sometime in the next couple months. Yeah. And then as a follow-up, the infill is it's a triangle. It's a two-dimensional triangle that propagates through the entire part. So basically imagine that you have like a document grid on a print bed, and your part occupies that grid. Where that part sits is the triangles will exist in the same on that. Someone asked again, can we print solid? We can print solid to a certain size. That size is not very large. It's probably about a centimeter. What do I expect about wear properties versus heat treatment versus forged and rolled? Again, so wear properties generally relate to hardness. So if the hardness is the same, which ours is roughly the same as wrought or rolled material, whatever you want to call it, that's 46 on the 600-degree temper versus 45. The wear properties should be very similar. The one thing that I would say is different is because we have the parts are not full infill. You might see something wear through if you heavily wore it, but I would not expect that in most applications. Let's see. Part size in millimeters. So there's a specific question about part size. I'm assuming that's in millimeters. So we can get you the data on the exact. I don't want to do the math on stage. But we can get you the data on specifically how many parts you could fit in the future. Just doing a super quicker back of the envelope calculation, I believe the answer is a lot. 17 by 14, if it's in millimeters, is a pretty small part. Someone asked what's the largest cube we can make, wash, and sinter. Again, we don't print solid infill, so with a solid infill, you could go in theory, but it probably wouldn't work. In terms of a standard cube, probably in terms of the sintering, the sintering smallest dimension I believe is 3.5 inches, so probably somewhere in that range, or 2.9 inches I think. So with the sintering, what the sinter want to be that since you do it probably get bigger and would be constrained by the size of the weight of the part. Yeah.
All right.
All right.
If you have any last minute questions, feel free to put them in now. I'm actually going to do a little screen share and show everyone where they can find the data sheet on the website.
Oh, there you go.
Let's open this up. All right. We're going to stop video as well because we don't need that here. So this is the Markforged website. If you go here under materials.
You can go up to the materials page, I think.
And metals. This is the metals page, and here you'll find all of the metals we have available now. So you'll see 17.4 pH stainless steel, and below it you'll see H13 Tool Steel. And if you click this Learn More button, this is where you can actually find the data sheet. So if you have any specific questions about the materials as we've covered today, this is a good place to find them. Another good resource is the actual Metal X page. If you are not as familiar with the Metal X, with the process, with the product and how it works, the Metal X page has a lot more detail on approximately how some parts come out, the hardware, the technology. So you design your part, you print it in the green state, as Daniel was saying, you sinter it, and you have your part. A little bit more about the materials. You'll notice that what we're doing is we're releasing materials incrementally. So we've always had kind of a policy of parts first, meaning we want to make sure that your parts print really, really well before we release a material. So we started with 17.4 stainless steel. We are now releasing H13. And we're going to be releasing materials incrementally as we develop them, test them, and ensure that you're going to get high quality, reliable prints every time. So it looks like there's just a couple more questions. Package price. So for the Metal X, the wash and the sinter, we're looking at $125,000 US for the entire package, and that gives you everything you need to print, wash, and sinter your parts. We are going to be, we have been recording today's webinar. We're going to be distributing the recording of the webinar to everyone via email. It's a bit of a busy week, so I would expect that maybe by the end of the week. If you have any specific questions that we did not get a chance to answer today, I would encourage you to visit us at markforged.com and actually get in touch with someone. We even have a little chat button here, and you can actually get right in touch with someone at the organization who can answer your specific questions. I think with that, we're going to close off today's webinar. Thank you all so much for joining us.
Yeah, thank you so much for your time, and hope I could answer some of the questions you had. And yeah, feel free to reach out via any channel. We'll make sure to send you all the stuff we had, as Marco said. But if you have any questions, feel free to send an email to feel free to shoot us an email. Feel free to reach out via any of the ways that Marco talked about. We can get you in contact with people that can talk more about the system, that can get you benchmarks, that can do all kinds of stuff that move you forward before the end of the year or in Q1.
All right. Thanks everyone so much for joining us. We hope you have a great rest of your day, and we look forward to seeing you at the next webinar. Bye-bye.